This lecture is about the scientific method, which is the main method that scientists use in order to be able to solve problems involving the real world and to try to figure out patterns and other behaviors that govern nature. Before we get to what scientists do, though, let's talk about the kind of problem solving that we do in our everyday lives. Number one example I could think of was the TV. Let's say you go home from school, you sit down on the couch, you pull out the remote control, you press the power button, and nothing happens. Well, you just made an observation. Nothing happened when you pressed the power button. The thing that a scientist would do would be, the scientist would question, why isn't the TV on? Because questioning is the very most basic step in the scientific method. If you can't question, if you can't be curious, if you can't say, why is this going on, you can't be a scientist. You got to be able to question. So let's question it. Why isn't the TV turning on? Then we'd probably come up with some guesses, some reasonable possibilities for why the TV didn't turn on. Possibility number one, there's no power because the cable's unplugged. Possibility number two, the remote control batteries are dead. Possibility number three, maybe I'm not aiming it at the TV properly. There's lots and lots of different possibilities. This is all the hypothesis. This is the guess. This is the reason why we think. Now, the prediction comes along when we say, okay, if I guess that the remote batteries are dead, then if I put new remote batteries in, the TV should work. So we're going to predict what would happen if we did an experiment. So let's do that. Let's actually do the experiment. Let's go get new batteries for our remote. Let's put them in. Let's put them in the remote control, press the power button, and nothing happened. Well, so we could come up with a new observation then. Nothing happened when I changed the remote batteries. That doesn't automatically say that the other hypothesis is right, but it does say, okay, now I got to go through this cycle again. I got to go come up with a new idea. I got to come up with a new prediction. I got to come up with a new experiment to do. I could go plug it in. I could go, maybe the remote's a universal remote control. It has to be reprogrammed. There's lots of possibilities. Okay, even I could try pressing the power button on the front of the TV. Okay, this is a problem-solving approach. This is essentially what scientists do in the lab. They find a problem. They want to be able to solve it because they're curious about how the world works, and so they go about designing an experiment, a hypothesis, a prediction, to try to figure out, okay, what's going on. All right, here's some aspects of the scientific method. The scientific method, first and foremost, is a problem-solving approach. It can only explain natural phenomena, and it tries to do so using logic. If something is not part of nature, or if something is not in the world that we can touch, taste, sense, feel, or at least measure using some equipment, you can't do science on it. Science cannot say anything about unicorns, for instance, because unicorns are not real, they're not in the real world. Scientists can also not say anything about, philosophical concepts like love. Well, you can talk about biochemical love, because that would be love expressed in chemicals in the brain, but they can't talk about love as a human emotion, exactly, because it's not something that's necessarily testable. All right. The explanation is only good as its ability to predict the results of future experiments. Meteorologists do predictions every day. They have made these great scientific theories and scientific models about how the atmosphere works. They go plug in all those models and theories together every day, and they churn them out in a supercomputer, and they come up with new and exciting predictions of their theories every single day. And we know right away whether their predictions were right, because the experiment is the weather, and the weather will either fit their prediction the next day or not fit their prediction. So they have a pretty easy job because the experiments just happen naturally, and they just try to come up with the predictions based on hypotheses and theories. All right, key thing about science is the results must be reproducible. If your results only work for a very narrow set of circumstances, it's probably not a very good theory. It's probably not a very good hypothesis. Anyone has to be able to do the experiment you did, come up with the same results. Anybody has to be able to use the theory that you came up with and come up with results that work. So reproducibility is at the heart of science. Finally, I want to say that science is inductive, not deductive. Inductive reasoning is when we start with facts and then we try to come up with a big idea, a big umbrella idea that encompasses all the facts. So it's bottom-up reasoning. It's, we start out with the little picayune details, and then we come up with the big grand statement that kind of summarizes them. The reverse of this is deductive reasoning. Deductive reasoning starts out with a big idea and then comes up with the details. So let's say, deductively, let me make the statement, parents love their children. Well, deductive reasoning would say, okay, then parents are going to make sure their children are bathed and fed and all this kind of stuff that comes out, we think, because of it. Whereas inductive reasoning would, you'd sit in a household, you'd watch what the parents are doing. The parents are taking care of the kids. And from that, you'd come up with the statement, parents love their children. So there are different methods of reasoning. Inductive reasoning starts with experiments, with facts, with observations, comes up with a theory, a big idea. Deductive reasoning starts with the big idea and comes up with, okay, this is why I think things are with it. So science is at its basis inductive. Scientists never have the theory first. They do the experiments first, and then they come up with the theory later. All right, I do want to say one more thing. Science cannot prove ideas true. Since it's inductive, all you can really do is say it's not false. In fact, true scientists are always going to try to falsify their theories. True scientists are going to try to run experiments that poke holes in their theories and try to prove their theory wrong. Because the way that things are proven in science is you do it again and again and again, and if it doesn't end up false, that means we're pretty certain that it's true. But we can never prove it's true 100%. 100% proof will never, ever, ever happen in science. There's always room for improvement. There's always room for try a new experiment. That doesn't mean that things are not, that science isn't useful. In fact, look at the world around you. TVs, cars, planes, televisions. I said that before. But anyway, all of these things are built because of scientific principles. So science is pretty darn useful, even if we can't prove things 100% true. We can prove things true enough that they work almost all the time, or all the time in our experience. All right, we're going to go to the steps in the scientific method now. These are my steps. Other people have different kind of names for them or different kind of combinations, but this is what we're going to use in our class. Observations are information from the senses or from measuring devices. We're constantly making observations. The question is, what sets the scientist apart from somebody who just says, scientists are always curious. And then they come up with guesses to explain their observations. And then they probably come up with predictions. If I do this, then that will happen. Prediction's actually a really important part because it means that you're not just randomly mixing stuff. Predictions are when you come up with ways to falsify your theory or falsify your guess. And finally, you do the experiment. You test the observation in a controlled manner, and that will tell you, is it correct? Is your prediction correct or not? And you get more observations, so it's actually a big cycle. Hey, how about that? So a scientist might go through this cycle thousands of times in a career or even in just a project. Okay, two ideas related to science are that of the scientific law and the scientific theory. Laws and theories are different. Here's the difference. Laws summarize, theories explain. Okay, what that means is laws, what they do is they just say, this is what happened in all my observations. So they're usually mathematical in nature. They describe experiments using math and equations. They do not explain anything. So the example I have down here is Isaac Newton. He came up with laws of gravitation. He came up with equations that described how gravity worked. They described if you shot a bullet through the air, this is how long it will take to hit the ground. If you drop an object, this is what position it'll be at a certain time. He didn't know what gravity was, though. What is gravity? Well, Isaac Newton had no idea what actually caused gravity. He didn't have no idea for the explanation for gravity, but he knew how to model it using math. He knew how to summarize how every object anywhere on Earth would fall, or even in the sky would go around other planets and that kind of thing. Okay, so this is Newton's law of gravitation, just in case you want to know. You're going to learn it next year in physics class. Okay, scientific theories, on the other hand, are explanations. They try to describe the relationships among a lot of observations, make definite predictions about future observations. They're similar to models. Theories can be thrown out even if one experiment in 1,000 disproves them. So they're always being modified and added on. Theories are never set in stone, but if experiments keep backing them up, if experiments keep not falsifying them, then we're going to rely on them. Richard Feynman said something great about experiments. Experiments and theories should always take in all the information, not just on the information that you're focusing on. You should disclose everything, because theories have to predict future experiments too. The finished theory should always make something else come out right, not just what you've worked on, but what other people will do in the future. This would not be a scientist. Scientists don't say, only my information is right. Scientists say, anyone in the world should be able to work with my data and my theory and come up with the same conclusions I can and extend them to the future. Okay, all models are wrong, but some are useful. Models are simplified examples of reality. They're not the real thing. We're going to build lots of models this year. Models help us explain and kind of work through data. Simplified representations to use to make predictions. And they can be visual, they can be mathematical, they can be on supercomputers, they can be devices. Okay, how you judge a model, these are some criteria. We're not going to go into it too much, but I just wanted to point out that theories and models go with hypotheses and laws go with observations. So just remember, laws describe, theories explain. When you design an experiment, you're going to want to control your variables really well, so you want to write down this information. You want to focus on only one thing at a time. That's your independent variable and your dependent variable. So change one thing, focus on one other thing, and control everything else. Thank you for watching.